So I'm working at a company called IOHK, and what do? Our flagship product is a cryptocurrency, and that's something where real money is at stake. So you should better be careful to make sure that things work correctly and stuff works as expected, because otherwise people lose money and they get very angry. So what do we do to make sure that our software is correct? Well, obviously we use Haskell, so we have a strong type system and we have functional programming, and so then that's unfortunately that's not quite enough. So because you can write Haskell code that is wrong. So what we also do is we make extensive use of quick check to write properties, as we were explaining yesterday evening, and that's a very nice technique. Unfortunately, sometimes it's still not enough. So we want to do even better, and we want to use formal methods and specify what the code should do, and then ideally also get proofs that the code actually adheres to what the specification does and that the specification has the properties that we want. So we'll try to see how far we can get there, and basically mix all the things that we can do. And IOHK is strongly committed to using formal methods, so we have a team of specialists just doing formal methods, and we let them work on our flagship product, which is not something that everybody in industry would do. And but still, we're industry, so we also have to be agile. So and the bottom line of the talk basically is going to be that those two don't have to be a contradiction. So you can do both, and actually it's very good to do both, and using formal methods can actually help you to react to changing requirements very well. So just to set the scene, let me just explain to you very briefly what a cryptocurrency is. So you want to have digital money, so you want to have some ledger that basically registers transactions that the users send. But you don't want to have that on one central computer, because then one party is basically of control of all the money. But you want to have a network of computers, and they all carry the same ledger, and they basically make sure that no one can forge the ledger or remove transactions or block transactions or something like that. So it's not a very, so you use here different computers not to be more efficient, but basically to be more resilient. And how do you do that? How do you distribute basically the responsibility to maintain the ledger? You do that by taking turns in collecting transactions into blocks, and then each block has a reference to the last block, and then you send those through the network. So it's basically a linked list containing transactions. And what can happen now is that sometimes you get competing blocks that both link back to the same block, and that can happen either somebody's trying to do nefarious things, or just if the network performance, for instance, is not good enough, then the person producing the block didn't get the last one, and so you get forks in the system. But then after a while, the next person producing a block basically just picks one to continue with, and then after a while those forks get resolved and you have eventual consistency. Now, of course, since you don't want to have this be a permission system where you have a fixed set of participants, this notion of taking turns is not that trivial, so you need protocols to determine who is allowed to do the next block. And so the most prominent one is this proof of work that Bitcoin does, where you do calculations and then basically waste a lot of energy just to determine who can produce the next block. What we're using is something called proof of stake, which basically looks at the ledger, and then the more money you have in the system, the better your probability of being able to create a block. And so our researchers, they produced the protocol called Ouroboros, which is the first provably secure proof of stake protocol, and we're using that to implement Cardano. Now, building this is not an easy task, because it's a distributed system. It's in a highly adversarial setting. So everybody should be able to join the network, and people will want to attack it because there's real money in it. So you have to be careful what you do there. And it's also performance critical, because, as I said, if the network performance is too bad, then you don't get blocks quickly enough through the system, and you get these forks. So you have to worry about a lot of things. So you want to have this correct, and not only do you want this to be correct, but you also want to be able to show to people who want to use this that it is correct, and show them some evidence that really you did the right thing. And that's then, to make matters worse, this is a quickly moving, rather new field, so there's new ideas all the time, and sometimes you get told, okay, we have to do this as well, so your requirements are changing, not all the time, but they do change from time to time. And so, yeah, you can't just sit down and gather all the requirements and then start implementing and hope that nothing changes. So yeah, in order to do things correctly, we're using formal methods. And if you're working in industry and you're telling your manager that you're using formal methods, then what they might be thinking of is just this process where you have some time where you gather all the requirements and then you write a specification. Then you do a proof that you fulfill all the requirements, and then you write code, and then you prove that the code adheres to the specification. And so there's a long time between starting something and having something that you can use. And what they might tell you to do instead is be agile. So produce something quickly and then iterate and iterate and iterate, and eventually at some point we're good enough. The problem with this, of course, is that if you're not careful in all the steps, I mean, if you're doing something where there's no value at risk, then you can afford having some bugs and removing the bugs by iteration. But that's not the case in cryptocurrencies, because if you have a bug, then people steal your money, and that's that. And yeah, of course, this at the bottom, it's just a caricature of a process that nobody would really want to use. And what we're really meaning when we're using formal methods is that we use a mixture of a lot of methods that all help us to produce code that works and that we're confident in. So we use models, we simulate stuff, we do write specifications, and in particular executable specifications, which I will come to in a moment. We use quick check, we use proofs, and there's also a lot of feedback. So when writing executable specifications, we sometimes see that something in the original specification needs to be changed. So it's fairly more closely to that one, but with different techniques than what you do in everyday software development. So let's talk a bit about the architecture of what we're building. So you have this object, this blockchain, where you have in blue, these are the transactions that you're interested in. And then in order to determine the validity and get consensus, you have this block structure around it. And the first thing that we want to do is separate those two, because in the ledger, we want to do bookkeeping. And we don't want to worry about, okay, these transactions that I have in the ledger, I have to remove them again because they were in a block that got rolled back. That's something that we want to separate. So we have the consensus layer that basically looks at the shape of the chains and which one is the longest and which one is valid and so forth. And then the consensus layer tells the ledger basically, these are all the transactions, and apply them in a linear fashion, and then that's the state. Then, of course, we have other components for storage and for networking, all of those things that you need. And what we decided for the interactions between components is to have the ledger just interact with the consensus, not with all those low-level components at all. And furthermore, we want to have the ledger just consist of pure functions where you can easily reason about them and do equational reasoning and do quick check as explained yesterday evening, as opposed to with effects and interactions with the outside world that you don't have under control. So we put all the interactions with the outside world, all the I/O stuff in the consensus layer and below, and the ledger is just pure and it gets all the information that it needs from the consensus layer. And then we can look at the individual components and make a decision, what kind of methods do we want to employ, what kind of methods can we employ in order to get this out of the door. And for the ledger, this is the central piece. If we screw that up, then that's it. Then the money is gone, and people can do things like create money or steal money or things like that. So it really has to be correct. Now, of course, you could say getting ledger correct is not that hard. The Medici did that hundreds of years ago. So why are you worried? But this is actually a bit more complicated than just having to worry about people sending transactions and inserting them into the ledger. There's lots of stuff going on in the background that the system has to do on its own. So every time you create a block, you get some rewards for that, and then those have to be distributed automatically. Then you have monetary expansion, that there is some kind of money being created all the time into the system, injected into the system, and all of these things. So the individual things that can happen in the ledger are all fairly simple, but the interplay between those, they're not, because it's just a lot of rules. And what we decided to do to implement the ledger is to specify the behavior on the microscopic scale in terms of small step transition rules. That just corresponds to pure Haskell functions. And then in order to get the overall behavior of the ledger right, we specify properties that the ledger should have, something like the total amount of money is conserved and there's no money created out of thin air, instead for this, this monetary expansion that is controlled and stuff like that. And then we can convince ourselves that those properties are fulfilled by using quick check, manual proofs on pen and paper, or even formal proofs in Isabelle. Now I want to take you a bit through the process of what does that mean? How do we get from the idea of what the ledger should do to the formal specification? And how do we get from there to working code? And so the first step is really, once you have the ideas of what the ledger should do, you want to write it down in an unambiguous way. And once you do that, lots of questions pop up, because once you write stuff down in mathematical notation, there's no room for ambiguity. So you have to really answer all the questions that otherwise, if you're just talking about it, you might not even realize that they're there. So that's what you do, and then eventually you end up with something that looks like this. And so just maybe show of hands who's familiar with this kind of notation. Is it? Okay. That's better than at the last conference I taught this. But so maybe just to talk the rest of it through it. What's described here is a transition rule for the state of the ledger. And so below the bar here, you have basically the way that the ledger state moves from one state to another. And this UTXO, that's basically all the money that's in the system. So the way that accounting works in the system is you have lots of piles of money, and then a transaction takes some of those piles, destroys them, and creates new piles of money. And so that's just what's written here. So the UTXO, that's this set of unspent transaction outputs, so all the piles of money that are still there. You take them and you remove everything that the transaction uses as inputs, and you add all the outputs from the transaction to it. And of course, if that were all that it took, then you could just create arbitrary amounts of money, but you have some conditions to satisfy here. So you require that all the inputs from the transactions are actually in the UTXO before you make the state transition. You require that the transaction is balanced, so that you look at how many money goes into that, how much money goes out of it, and that has to be the same. And then also you have to worry about fees and stuff like that. And then that's basically, and you have some environment that specifies like what are the fees for a transaction and stuff like that. And then this is basically rule. So above the bar you have the predicates that must be fulfilled in order for this rule to be fired. And then below it you have the description of how the rule, what the rule actually does. And then you can compose those rules and you can say, okay, this is the rule from up here, and you can say, if you have a transaction that actually is signed and carries proof that people can actually use those inputs, then yeah, you have this rule plus some other constraints. And yeah, that's basically that. So can I get another show of hands? Has the number of people familiar with this notation increased? Yeah, okay, good. Right. Then the next step is translating that into Haskell. So until now, this was just a LaTeX document, which is very good for talking about this because it makes everything explicit, and you can explain the syntax even if it's a bit unfamiliar at first to most people. It's something that you can easily teach other people to read, and you can talk with that about. You can talk about those things using that notation with the researchers, with product management, with everybody who's like interested in understanding what's going on, and you can get sign off that this is actually what people want. And then the next step is translating that into Haskell code, and that's the nice thing about Haskell. It's just the translation is really very natural. So we have a small library where we basically allow expressing these things, and it's just if you just read these things, apart from there being a Unicode subset and here just a subset of function, it's really nearly the same. And then we annotate it with like some information in case that the rule cannot fire. We want to know why it can't fire, so we increase some labels. We add some labels there. But that's basically it. And then this is the same specification that we wrote down, but it is executable. And that's really very valuable because on the one hand, the type checker tells us if we screwed up, and on the other hand, it's actually the basis for the production implementation. So you have an implementation at that point. It's not yet the one that you want to use because it still abstracts over a lot of things. It doesn't store anything on disk, and it might not be optimal or something. But it is the implementation. It is the basis for the implementation, and the logic is there. So how does the development process, what kind of activities do you do over time? So in the beginning, if you do this approach, you write down some prose documents, and these could be research papers or design documents or whatever, and you explain how the system should work. Then from there you go to the specification, and there's a feedback between those two, because sometimes when you specify things, you realize that you have to actually make some modifications there. And there's an even tighter coupling between the executable specification and the specification, because you get the type checking once you do it executable. And then you write quick check tests. You do that in parallel, like explained yesterday evening in this property-driven development thing. And then, up until here, there's still, things are pretty much in flux, because you realize that the design maybe wasn't perfect until it stabilizes to some point. And then, once it's stable, you can start adding proofs, because you don't want to do the proofs up front, because if something changes in your design, you have to do the proofs all over again. With the quick check properties, it's just you run quick check again, and if it still works, then it still works. And if not, then you have a problem. And yeah, so that's basically how it works. So it's a tightly coupled thing. You do lots of things in parallel, and each of those streams basically informs one or two or more of the others. So let's just compare this methodology with what other people do, and let's use the example of building a bridge. So if you have a civil engineer building a bridge, they sit down at their desk and they do a lot of planning, and they get a building permission, they order like a land survey, and then after all that is done, then they actually build the bridge. And that's nice, and that's the way that you should build bridges, because if you do anything wrong in the planning, then you will not end up with any bridge at all, or with one that collapses when people walk over it. So that's actually the right process there. But if you look at that from the outside, then for a long time it looks as if nothing was happening at all, because there's just people sitting at desks. If you do traditional agile software engineering, then you do a sprint, you create a pillar, you do another sprint, do another pillar, you build the bridge, and then you do some maintenance sprints in order to get everything fitting, and yeah, that's that. If you start from an executable specification, and that's in a way that's also great, because you can continue to demonstrate progress. Always there's something going on, so you can demonstrate that you're building something, and there's high confidence that eventually you get everything done. But the end result is maybe not the most beautiful thing that you might wish for. If you start from an executable specification, you basically just put the bridge into thin air. You don't worry about pillars at all. You abstract away from them, and you get the high-level construct first to something that is working. And then once you have that, you can add all the pillars that you like. And the nice thing is that if you do it like that, you solve the hard problems first. And you really want to do that, because if you solve the easy problems first, you might make decisions that make your hard problems even harder than they were to begin with. And so you don't want to do that. And but at the same time, you have working code pretty early. As soon as you have an executable specification, you can show it. You can execute it and show it to your stakeholders and show that you are making progress. And then you can, as you fill in the gaps, as you remove the abstractions, you can show that you have solved another thing. And that's really very good. The consensus thing, unfortunately, is harder. Oh, 1 minute? OK. So the thing is, it's really hard to get concurrency right, and it's even harder to get guarantees that it's right. And the right thing to do would be to express it just in process calculus, and then prove that it's correct, and then calculate it against the process calculus. What we did as an alternative was just to emphasize testability early on in the design process, and then use simulations and verify the design, and then test with quick check. And actually, what we're doing is both. So we start with doing this, and we have another team working on a formulation and process calculus. And this allows us to do formalization proofs, but we're not blocked by it. We have something working, and something that we have high confidence in, but not optimal confidence in, and then we can fill in the gaps later. The thing is, with quick check and stateful code, and in particular concurrent code and code that interacts with the outside world, it's really hard to find bugs because they're intermittent. It's harder to reproduce them, and it's impossible to shrink them. So what we do instead in order to make it reproducible and deterministic, is that we run our code in simulation. And if we do that, then we can reproduce the bugs, we can shrink the test cases, because the simulation is deterministic. And yeah, of course we want this to be the same code that we're also having running in the original system. And we do that with a library where we basically define type classes for all the functionality that we want. So for something like getting the current time, and we make I/O an instance of that, but also a simulation monad. And then we do the same for async and STM. And then if we run it in I/O, we actually execute the code. But for the tests, we run it in a simulation, and then it is deterministic. We can shrink the test cases. We can actually alter the environment to make it more likely to hit some race conditions or stuff like that, and that's very convenient. It's not only good for testing, it's also good for predicting performance. If you have something, if you want to model something and you want to know how fast it is, then this simulation is also very useful because it's timing accurate. So the conclusions is basically you want to be flexible in what methods you apply, and which methods you apply where depends on how critical the component is and how complicated it is, because some methods are just, yeah, you have to compromise sometimes, and yeah, we do that. The goal is to move quickly but not break things, and then always leave room to follow up with more formal techniques that are maybe slower but that further increase your confidence. And yeah, the bottom line is that this formal versus agile thing that you sometimes hear is really a false dichotomy, and in fact, formal methods can help you being more agile, and that if you have this formal specification and the quick check tests and everything, then yeah, you can react to changing requirements quite well. Thank you.